July 12, 2022. A dataset arrived that would unsettle modern cosmology. Inside a public data release from JWST's first deep imaging campaign lay something wrong. A point of red light in the constellation Cetus, impossibly bright for its measured distance. Astronomers at the University of Florence named it Glass Z13 and ran the numbers twice. The galaxy existed 320 million years after the Big Bang, when the universe was barely formed. At that age, the cosmos was supposed to be a dark, chaotic fog of collapsing hydrogen gas. No structure that large, no object that bright should have assembled so quickly from nothing. Yet Glass Z13 burned with the light of hundreds of millions of stars already blazing steadily. Its redshift, Z equals 13, meant light traveling 13.4 billion years to reach JWST's mirror. That number placed the galaxy in territory no instrument had reached before this telescope. Hubble had glimpsed objects at Z equals 11, the previous record pushed by its infrared camera. But Z equals 13 was a different epoch entirely, 100 million years earlier in cosmic time. The gap between those two numbers contains an entirely different universe than the one we modeled. Before Glass Z13, astronomers assumed that gap held only small, dim, fragmentary proto-galaxies. Afterward, they had to admit they did not know what lived in those earliest epochs at all. This single galaxy triggered a cascade of questions cosmology is still struggling to answer today. 6 months before that discovery, a rocket stood on a launch pad in French Guiana waiting. December 25, 2021. Scientists around the world held their breath as countdown reached 0. The Ariane 5 rocket carried the most expensive science instrument humanity had ever constructed. 25 years of engineering, $10 billion, and the ambitions of an entire discipline. The James Webb Space Telescope traveled not to Earth orbit, but to 1.5 million kilometers out. At the second Lagrange point, gravity from Earth and Sun balance perfectly for a stable hold. JWST unfurled a 5-layer sunshield the size of a tennis court, stretched impossibly thin. One side faces the sun, reaching 85 degrees Celsius in constant, unfiltered bombardment. The other faces the void, cooling to minus 233 degrees Celsius in permanent shadow behind the shield. The telescope's instruments settled at their required temperatures, cold enough to see the invisible. Its primary mirror, 6.5 meters of gold-coated beryllium, reflected infrared light with precision. Gold reflects infrared efficiently. The light stretched by 13 billion years of cosmic travel. By June 2022, the SEERS program began, Cosmic Evolution, Early Release Science, across Ursa Major. NIRCam captured the target field in multiple filters, collecting photons over long exposure hours. When images downloaded to Earth, red dots appeared scattered across the field unexpectedly. Bright where they should be faint. Massive where models had confidently predicted small and dim. To understand why these dots mattered, you must first understand what should have been there instead. The Lambda CDM model has governed cosmology since the 1990s, confirmed across thousands of observations. Lambda is the cosmological constant, the energy density of empty space driving cosmic acceleration. CDM is cold, dark matter, invisible particles that feel only gravity and move slowly through space. Together they describe a universe that begins simple and grows complex through gradual assembly. At the Big Bang, the cosmos was a near-perfect, hot, dense plasma, almost completely smooth and uniform. Quantum fluctuations, amplified by inflation, seeded the tiny overdensities that grew into all structure. Dark matter fell into those overdensities first, gas followed, and the first stars ignited 100 million years later. Supernovae from those first stars heated surrounding gas, slowing further collapse through feedback. Galaxies then grew slowly by merging with smaller systems and accreting gas across billions of years. Computer simulations running lambda CDM physics predict this process follows a strict, specific timeline. At 300 million years post-Big Bang, galaxies should contain at most millions of solar masses total. Billions of solar masses, comparable to the Milky Way, should not appear for at least a billion years. When Glass Z13 appeared at 320 million years, carrying hundreds of millions of stellar solar masses, the numbers did not fit. The timeline collapsed, and theorists began searching urgently for answers. Dr. Ivo Lebay at Swinburne University in Australia downloaded the public CEERS data immediately. His team applied photometric redshift analysis, measuring each galaxy's distance from its color. Light from distant objects stretches to longer wavelengths as expanding space pulls it toward red. The redder a galaxy appears across infrared filters, the farther it lies, the earlier its epoch. Among hundreds of candidates, 6 galaxies stood apart from every prediction the team had encountered. Each of the 6 showed redshifts between Z equals 7.4 and Z equals 9.1 across independent filters. In cosmic time, those redshifts placed the galaxies between 500 and 700 million years post-Big Bang. That epoch is less than 5% of the universe's current 13.8 billion year lifespan. Still infancy. What was not expected was the mass those galaxies contained within their compact, burning cores. The most massive of the 6 contained between 60 and 100 billion solar masses of accumulated stars. That figure is comparable to the Milky Way, which took 13 billion years to build itself to that size. These 6 galaxies had assembled equivalent mass in under 700 million years of total cosmic time. Dr. Labay's team rechecked every calculation, adjusted dust models, tested different formation histories. The masses stayed high across every assumption, violating predictions not by margins, but by large factors. On February 22, 2023, their paper appeared in Nature, with a deliberately cautious and careful title, A Population of Red, Massive Candidate Galaxies at Z greater than 5. The astronomy community called them something else in conference rooms and informal discussions afterward. Universe breakers. Galaxies that shatter our understanding of how the cosmos assembles from nothing. Dr. Joel Leha at Penn State ran independent analyses and confirmed the mass estimates consistently held. Dr. Erica Nelson at the University of Colorado examined their shapes in high-resolution JWST images. The galaxies appeared compact and dense, not the extended diffuse structures cosmological models predicted. Dr. Catherine Whitaker at UMass Amherst calculated star formation rates from the observed stellar masses. If these galaxies formed all their stars in 500 million years, those rates must be truly extreme. Perhaps 100 to 1,000 solar masses per year, against the Milky Way's current gentle rate of about 2. But photometric redshifts remain estimates. Colors can be deceived, the community reminded itself. Dust can redden a nearby galaxy to mimic a distant one with surprising photometric accuracy. Active black holes emit light that overwhelms host galaxies, inflating apparent stellar mass estimates. Only spectroscopy could resolve the ambiguity. splitting light into precise wavelengths for direct measurement. JWST carries NIR spec, the near-infrared spectrograph, designed for exactly this moment of uncertainty. Unlike cameras measuring brightness in bands, spectrographs reveal emission lines at precise wavelengths. Hydrogen emits light at 121.6 nanometers at rest, a fixed property of atomic physics everywhere. Measuring that line, shifted to 972.8 nanometers, places the galaxy at exactly z equals 7, unambiguously. No dust model, no AGN contamination can change a spectroscopic redshift once precisely measured. By late 2023, follow-up programs began targeting the 6 massive galaxy candidates for spectroscopy. The first confirmed results arrived in December 2023, and they were completely unambiguous in outcome. 4 of the 6 received spectroscopic confirmation of their estimated redshifts with full certainty. Z equals 7.6, Z equals 8.5, Z equals 9.0, and Z equals 9.1, exactly as the colors had suggested. Genuinely ancient, genuinely massive, genuinely impossible, according to every standard cosmological model. 2 of the 6 proved to be misidentified, lower redshift galaxies reddened by dust and AGN emission. Still scientifically interesting, but not universe breakers. Not violations of fundamental cosmology. 4 remained confirmed. 4 galaxies existing 500 to 650 million years after the Big Bang with certainty. Spectroscopy had made the problem worse by removing the last escape route of measurement error entirely. The question was no longer whether these galaxies existed. It was how they formed so impossibly quickly. The theoretical community began proposing solutions before the spectroscopic confirmations even arrived. The first hypothesis focused on star formation efficiency, perhaps far higher in the early universe. Modern galaxies achieve roughly 10% efficiency, leaving 90% of gas unconverted to stars. If early galaxies converted 50 or 70%, more mass would accumulate in less cosmic time. But stellar feedback prevents efficiency from climbing so high under any known physical scenario. Massive stars form first, explode as supernovae within millions of years, heating and dispersing gas. This self-regulating mechanism appears in every simulation, every galaxy observed across every epoch. No proposed mechanism could suppress it selectively in early epochs without affecting later observations. The second hypothesis proposed a top-heavy initial mass function in the earliest stellar populations. If early galaxies formed primarily massive stars, they would appear brighter without requiring more total mass. Massive stars are hundreds of times more luminous than small stars for the same amount of stellar material. But massive stars die quickly. Follow-up JWST observations showed the universe breakers not fading. Their light remained bright across multiple observing epochs, contradicting what the top-heavy IMF predicts. The third hypothesis turned to dark matter, the invisible scaffolding that structures the entire cosmos. Perhaps dark matter halos in the early universe formed faster or larger than current simulations predict. Larger halos pull in more gas gravitationally, enabling more star formation in the same amount of time. But dark matter properties affect all of cosmic history. Tweaking them breaks later confirmed predictions. The modification cannot be isolated to the first billion years without propagating damage through time. The fourth hypothesis proposed supermassive black holes rather than stars produced the observed luminosity. If active galactic nuclei power the brightness, the stellar mass estimates would be drastically overestimated. But growing billion solar mass black holes in 500 million years violates black hole growth models equally. Starting from stellar progenitors at 100 solar masses leaves an impossibly short window for growth. Reaching a billion solar masses requires continuous maximal accretion across every second of 400 million years. The problem does not dissolve by attributing mass to black holes. It simply changes shape and grows harder. In 2023, a discovery from a different research direction amplified the crisis from a separate angle entirely. Priyamvada Natarajan and Akos Bogdan at the Harvard-Smithsonian Center for Astrophysics published a landmark result. They combined JWST near-infrared observations with archival Chandra X-ray telescope data of the same sky regions. X-rays trace energetic processes, specifically radiation from matter falling rapidly into active black holes. Their analysis revealed quasars at redshifts above z=10, objects from less than 500 million years post-bang. Some carried black hole masses approaching 10 billion solar masses at that impossibly early cosmic epoch. Standard black hole growth begins from stellar remnants of roughly 100 solar masses after stellar death. Growing from 100 to 10 billion solar masses requires a factor increase of 100 million in total mass. Even at maximum possible accretion rates, this growth requires more time than 500 million years allows. Natarajan and Bogdan proposed direct collapse black holes, an alternative formation pathway for earliest seeds. Instead of forming through stellar deaths, primordial gas clouds collapse directly to black holes entirely. Direct collapse produces seeds of 10,000 to 100,000 solar masses, dramatically reducing the required growth factor. But direct collapse requires rare conditions: low metallicity gas, strong ultraviolet fields, precise coincidence. Finding enough such events to seed the observed abundance of massive early black holes remains deeply problematic. The early universe was productive in ways that neither galaxy formation nor black hole physics easily explains. Both problems demand solutions simultaneously that existing cosmological theory cannot provide without contradiction. By mid-2024, the cumulative weight of evidence had pushed cosmology into genuinely uncomfortable territory. Over 30 galaxies had been spectroscopically confirmed at redshifts above z=7 by multiple independent teams. The universe breakers were not an isolated fluke. They represented a systematic and genuine population throughout. In July 2024, JWST confirmed a galaxy at redshift z=14.32, just 280 million years after the Big Bang. At that epoch, the universe was barely 2% of its current age, a fog of primordial gas barely collapsing. Yet this galaxy already contained several hundred million solar masses of stars burning in the primordial dark. Dr. Dan Koh at Johns Hopkins analyzed cumulative data from all confirmed high redshift galaxy survey programs. He calculated that the number density of massive early galaxies exceeded model predictions consistently. Not by refinable margins, where systematic error could explain the gap with careful recalibration. By factors of 5 to 10 in some redshift bins, too large for any parameter adjustment to bridge adequately. Dr. Michael Boylan-Colchin at the University of Texas published a quantitative analysis in August 2024. He showed that forming these galaxies required converting nearly all available baryonic matter into stars. Not 10% efficiency, not 50%, approaching 100% in the earliest dark matter halos. 100% star formation efficiency is physically implausible given what we understand about feedback. Boylan-Colchin concluded that lambda CDM, as currently formulated, cannot explain these observed objects. For a model that had explained essentially everything measured across 3 decades of precision cosmology, that was an extraordinary and unprecedented conclusion to reach about the standard model of the cosmos. The cosmic microwave background, galaxy clustering, supernovae distances, lambda CDM succeeds across all of these. But the first billion years, now directly observable through JWST, appears to operate by different rules. Exotic theoretical proposals began entering the scientific literature as the evidence mounted through 2024. Primordial black holes formed during inflation could have seeded galaxy formation long before the first stars. If black holes formed in the very early universe at masses of thousands of solar masses, galaxies nucleate faster. Warm dark matter was proposed as an alternative, particles moving faster, changing early collapse timescales. Modified gravity theories suggested that gravitational attraction strengthened at specific early cosmic epochs. Each proposal that fixed the early galaxy problem introduced new tensions elsewhere in the cosmological data. Lambda CDM is a web of interconnected predictions. Pulling one thread unravels others that fit data perfectly. No modification proposed through 2024 has resolved the early galaxy tension without introducing new contradictions. What does it mean when the most successful scientific model in history fails at the very beginning of time? The answer, stated honestly, is that it means the model is incomplete. Not wrong, but incomplete. Lambda CDM was not built carelessly. It represents the synthesis of a century of extraordinary observational work. Both the standard model of particle physics and Lambda CDM succeed brilliantly across their tested domains. Both are also acknowledged to be incomplete, missing fundamental elements that future physics must provide. The standard model cannot explain dark matter, dark energy, or how gravity fits into the quantum world. Lambda CDM cannot now explain what JWST finds in the universe's first billion years of existence. Dr. Adam Rees, whose supernova measurements first detected cosmic acceleration, described the situation carefully. Models are not truth, he noted in a 2024 lecture. They are our best approximations of truth at any moment. When data contradicts models consistently across independent observations by multiple teams using multiple methods, data wins, and models must evolve, not the other way around, however elegant those models seemed. Science advances not by defending theories against uncomfortable data, but by following that data into the unknown. The universe breakers are not anomalies demanding dismissal through clever, systematic error reinterpretation. They are messages from the first billion years, the cosmos telling us our picture of infancy was incomplete. We are at a turning point, comparable to when Hubble discovered that galaxies lay outside the Milky Way entirely. When the universe revealed its true scale in 1924, cosmology had to rebuild its foundations from first principles. When Penzias and Wilson detected the cosmic microwave background in 1965, the Big Bang became established as fact. When Rees, Perlmutter, and Schmidt found the universe accelerating in 1998, everything about its future changed. Each turning point forced cosmology to expand its conceptual framework to accommodate unexpected new reality. JWST is delivering the next turning point, centered on the first billion years of cosmic time specifically. The universe's infancy, previously accessible only through theory and simulation, is now visible in direct observation. And what we see there does not match the predictions generated by our most successful cosmological model. The textbooks that students read in 2050 will describe a different early universe than those written before 2022, not because JWST failed, but because it succeeded more profoundly than our models could accommodate. The mystery of the universe breakers will be solved not by defending existing theory, but by genuinely extending it. Future observations with JWST, with the extremely large telescope rising in Chile's Atacama Desert now, with the Nancy Grace Roman Space Telescope, with instruments not yet designed for questions not yet fully formed. The next generation of cosmologists, some of them children today, will solve what Glass Z13 first posed. They will build models explaining not only the modern universe, but its impossible and violent infancy. When they do, our picture of where everything came from will be deeper, more accurate, and more astonishing. Glass Z13 is one sentence in that story, one data point from a galaxy 13.4 billion light-years away. But that sentence contained a revelation. The story begins faster and stranger than we had imagined it did. And the courage to follow that revelation, wherever it leads, is what has always defined science at its best. Thank you for staying with us until the very end of this journey through deep time. If this exploration moved you, subscribe and stay for the next ancient chapter. Your curiosity is what keeps these lost worlds alive.